Okay, let's start. So today in class, we're going to talk about relative motion of two particles, and in order to motivate this, let me tell you why we would be interested in understanding relative motion of two particles. So 12. 12.10 relative motion of two particles. Okay, so let's say that you want to, let's say it's a space shuttle, okay, and the space shuttle there is, people are moving in the space shuttle. Let's say this is a frame fixed to the space shuttle. And so let's say this is Earth, and this is something or a person in the space shuttle. Now, it makes more sense to first find the motion of the person with respect to a frame fixed to the space shuttle, right? And if you know the motion of the space shuttle with respect to the Earth, then you pretty much can determine how the person is moving with respect to the Earth, right? So this is an easy way of keeping track of motions. You don't have to always keep track of the motion of the person with respect to Earth. It's much easier to do it when you're looking at this person inside the space shuttle. So this is what I'll call the ground or fixed reference frame. That is, for all practical purposes, we would like to think, at least when we're calculating the motion of bodies moving in space, that the Earth is fixed, not moving. This frame, x prime, y prime, z prime, which is, let's say, attached to the space shuttle, is actually moving. And clearly, when that moves, the person inside the space shuttle is going to also move. But he could have his own motion too, right? So RA is, so we call this B. This is the position of the person. A is the origin of the frame attached to the space shuttle, and this thing is my ground frame, which is 0. So I can draw a vector from O to A and O to B. And then I can join the vector from A to B. So RA. So we're going to use I would say a new notation, which is this thing here. RA is the vector from O to A. So the normal way we'll be defining position vectors in this class is we'll write this as RA with respect to O, which means that the vector goes from O to A, okay, O to A. Now, because we don't want to write, most of the time vectors are with respect to the origin, we will not keep writing O all the time. So we'll just skip the O and we'll just write it as RA. But whenever I write RA, you should understand that it's with respect to the origin O, okay? So this vector, as you can see, the arrow points from O to A. Similarly, RB is RB with respect to O, and it's a vector from O to B, and finally there's a vector from A to B, and in this case I will keep the A in place because it's the vector B now is not from O but it's from A. Okay, now we can use some basic vector algebra. The position vector RA, you can see RA is given by the sum of, sorry, I'm going to write a position vector of B because I'm interested in the motion of the person in the space shuttle with respect to the Earth. So RB is equal to RA plus RB with respect to A. The only reason I can do this addition is because from vector algebra, the vector 0 or O to B is the sum of O to A and A to B. Okay, that's the basic rule from algebra. This is a triangle, and you can get to B from A, or you can get it directly from B. So this is always true. Okay, and also note that this is A to B and not the other way. It will make a difference. The vector from A to B is the negative of the vector from B to A. So what this is also saying is that if you keep a track of the motion of the point B with respect to A, or the person in the space shuttle with respect to the space shuttle, and you keep a track of the motion of the space shuttle with respect to the Earth, then you can find the motion of the point B or the person on the space shuttle with respect to Earth by summing the two things up. It's a more convenient way of keeping track of motions when frames of motion are changing. So what we can do then is we can differentiate that expression. We can take the derivative with respect to time. If we differentiate that, we would have dRB dt is dRA dt plus dRB with respect to A dt, and so I'm going to write this as VB equals VA plus VB with respect to A. So this is the velocity formula, which is very similar to the position formula. Okay. Now, one thing to note is that this is true only when A, the vector, the frame attached to A, or you can think of the figure in the previous figure, the space shuttle is translating with respect to time. Okay, that is, it's moving in the X, Y, and Z direction. It's not rotating. Yeah, question. Everything here is R. Everything here is R. And not rotating. And actually, later on, we'll be talking about rotating frames too. But for now, assume that we're going to assume that A is only translating. It's not rotating. So what we can do next is we can find the acceleration by just differentiating the velocity. So A, B is A plus AB with respect to A. So the other way to think about B with respect to A is to think of A as fixed, it's not moving, and observe the motion of B with respect to A. So this can be interpreted as motion of B when A is stationary. Okay. In reality, A and B both are moving, but you can think of this as motion of B when A is fixed. And the same thing for A, B with respect to A. So this thing here, B with respect to A and acceleration as well as velocity is the relative motion of B with respect to A. It's telling you how the motion of B will change with respect to A. So if in the same example of the space shuttle, if the person is moving around, you can think that the space shuttle is stationary and observe the motion of B as it changes with respect to A, and that gives you how their relative motion stands out. It's basically the vector. It's basically this vector here. So I'm going to write that down here. R B with respect to A. If you like, you can write this down. This is R A. This is R B. So this vector here is the relative motion of B with respect to A. That's how B will change if you see it from here. Or in other words, if there was a person here sitting here and observing B, then this vector will tell you how B is moving with respect to A. Okay. Any questions on that? So let's just apply this on a couple of problems. Okay, so two boats leave the pier P right here at the same time and travel in the direction shown. Okay, you're given the velocities and you're given the angles from the x and y axis as shown. The velocities are constant as shown in the figure. Find velocity of boat A relative to boat B and the time when they are 1500 feet apart. So you're going to assume that the time t is 0 when the boats are at P. So they start at P together at the same time and move in different directions with different velocities. And then you're going to find one velocity of B. Sorry, it's velocity of A relative to B, not the other way around. And for second part, you want to find the time when say S, or the distance between them, is 1500 feet. So can you try to solve part 1? You're going to find VA with respect to B, and you're given velocity of A as well as velocity of B, right? You're given VA and VB. So it's just a matter of applying the formula. So try to solve part 1. Okay. Anybody get the answer?
I got 10.
You got 10? One sec, let me. So it'll be a vector as well as, it'll be a vector, so you need position and direction. So it'll be something like I plus something j, because this is a vector. So let's write uh, velocity of A is equal to velocity of B plus velocity of A with respect to B. Okay, so we are asked to find velocity of A with respect to B. So we need to find velocity of B and velocity of A. So velocity of A is, well, it's 40, but then 40 is only the magnitude. You need to find the direction too. So velocity of A is cosine of, let's see, cosine of, yeah, so this angle is 30, so this angle has to be 60 degrees. So cosine 60 degrees I plus 40 sine 60 degrees J equals velocity of B is 30 cosine, so this angle is 45 degrees, so cosine 45 degrees I plus 30 sine 45 degrees J plus VA with respect to B. So what we can do is move things around. We can move this part to the left and then solve for VA with respect to B. It comes out to be minus 1.21 I plus 30.43 J, and the units are, it's in feet per second, so feet per second. Okay, that solves part one. What about part two? So we got to find the time at which they would be 1500 feet apart. So remember, they start at 0 0, and then they start moving away from each other. And some point of time when the distance is 1500 feet, you got to find the time. Yeah, question.
Second question. So part one, you word it, find velocity of both A relative to B.
Mm-hmm.
Are you gonna want it in unit form or in like magnitude?
Uh,
Or will you like identify with how you read
so if I want the magnitude, then I would say give the magnitude.
Okay, but you said velocity.
Velocity, that means that you should, yeah.
Okay, thanks.
Okay, so how do we solve the second part? So they're moving with uniform speed, and they have what? They have, in time t they would be at a certain distance. When would they be 1500 square feet apart? So the hard way to do this is to actually find the position as a function of time, so s as a general at a general point of time, and find the same thing for both those boats, and then use the fact that the distance between those two is 1500. So you could do that, but there's a simpler way. So velocity of A with respect to B gives you the motion of A when B is at rest. So the distance s, so that basically is a metric of how far they will drift apart, instead of trying to individually solve for velocity of the position of A as a function of time and position of B as a function of time. What I mean by that is if the S, so distance apart, would simply be velocity of A with respect to B, magnitude times time. Okay. So S is 1500. The magnitude of VA with respect to B is square root of the x component, which is that, and the square plus the square root of, the square of the x component plus square of the y component times time, and so time comes out to be 1.26 second. Okay, as I said, this is just one way to do it. It's probably the simpler way. The other way to do it is you'll have to find S1, SA, there'll be an I and J, and there'll be SB, there'll be an I and J, and then you will find SA minus SB, there'll be an I plus J, and then 1500 would be square root of this thing square plus that thing here square. So this will be, to get this, you'll have to do integral VA T dt, and same for B, VB dt. So 1, 2. Okay, you can do that, but it will take more time. You have to individually solve for the distances for the two boards and then take the distance between them. Yeah, it'll be 0 to t. So this thing here will come out to be a function of time. Okay, any questions on this? Okay, so another problem. So at the instance shown, car A, okay, car A is right here. It's traveling on a straight portion of the road at 25 meters per second. So 25 meters per second. So the same instant there's a car B which is traveling at, so it's traveling on the circular path portion of the road at a speed of 15 meters per second. You're going to find the relative velocity of B with respect to A. Velocity of B with respect to A. So just like the previous problem, if you know the velocity of B and you know the velocity of A, then you can solve for velocity of B with respect to A. Or in other words, velocity of B with respect to A is velocity of B Okay, so we need to get those two things. So A is traveling. Okay, we're going to assume that it's traveling this way. This should have been given. well, I think it's kind of obvious, right? The front of the car is this side. Okay, so this is how they move. So I drew the vector which points in the direction in which A is moving. And I know that it moves at 25 meters per second. However, I would like to get the velocity in terms of a vector. So before I do that, I need to be able to, I need a coordinate frame, right? I cannot find velocity as a vector unless I have a coordinate frame. So let's say that the coordinate frame is like this. So if you're not given one in the exam or homework, you should assume one yourself. Okay, so given that, let's try to see if we can find velocity in the x and y component of the velocity. So what we're given is this line here makes an angle of 30 degrees. So this is 30 degrees, which means that this thing here is going to be 30 degrees. So velocity of A is 25, the magnitude, times the unit vector in the direction of motion of A. So a unit vector in this direction. So that's going to be, you need to resolve this vector in the x direction and also in the y direction. So the x direction is going to be simply cosine of 30 degrees I, and in the y direction, which is this, it's so the y direction is sine 30 degrees j. However, the j component is in the negative direction, right? So we assume j upwards is positive, like so, but this is negative. So that is the velocity of A. Next is the velocity of B. So again, B is moving in this fashion. So I'm going to draw another diagram for B. And B is moving at 15 meters per second. So in order to find the velocity of B, I do have the magnitude. I need to get the unit vector in the direction of B. So can I find the angle made by B with respect to the horizontal? If I do that, then it's essentially writing that formula here and proceeding. So let's see if we can do that. So this is 15 degrees. So B is like this, and my bad, sorry, this is not like this. So I draw this line. P is going this way. Now there's a property of the circle that if this is 15 degrees, then and this is a tangent, then this angle has to be 15 degrees. So this thing has to be 15 degrees. So this angle is so this angle has to be 15 degrees. So all I need to do is, this looks very similar to the first figure. So the unit vector in the x direction is cos 15 degrees I, and the unit vector in the y direction is sine 15 degrees j, and it also points in the negative j direction, so there's a negative sign. So given velocity of A and velocity of B, I can then subtract one from the other to get VA with respect to B that is simply minus 7.162 plus 8.618 J meters per second.
Is it A with respect to B or B with respect to A?
Oh, this is just a writing mistake. This is B with respect to A. It should be the same as this. So to get this, I took velocity of B and subtracted it from A. Okay, that's it. Any questions on this? Okay, so the last problem we'll be solving for today is this. Okay, so two cars are moving on a circular track as shown. The speed of A is 90 feet per second. And you're also given that it is increasing, and it's increasing its speed at the rate of 15 feet per second square, so it's actually accelerating as it's going. While B has a speed of 105 feet per second. And it's decreasing its speed at 25 feet per second square, which means that it's decelerating at 25 feet per second square. You're going to find the relative velocity of A with respect to B, or VA bar B, and acceleration of A with respect to B. So V A with respect to B is something which is asked, and acceleration of A with respect to B is also asked. Okay, so it's clear that if you want to solve for those things, so VA with respect to B is simply VA minus VB, and AA with respect to B is AA minus AB. So it just boils down to finding acceleration of A and B, and similarly velocity of A and B. So in order to find the velocity of A, we need the magnitude which is given to us. We also need the direction of velocity, and there is no coordinate frame on the figure, so I'm going to make up my own coordinate frame. So I'm going to just attach a coordinate frame right at the origin or the center of the circle. So that will help me to find velocity of A and B. So what is the velocity of A? What's the velocity? It's minus 90I, because 90 is the magnitude and it points in the direction opposite to that of I, so it's minus 90I. What about B? Its velocity is 105. Okay, but we need to also find the unit vector along B. So what I'll do is I'll draw B. And what else is given to me? You're given that B makes an angle of 60 degrees with the vertical. Okay, So it makes 60 degrees with the vertical. There's this property of a circle that is when B is moving, it moves tangential to the point where it is currently placed. So this angle here is 90 degrees because this vector here is tangent. So I'm going to draw a vertical line. Can you tell me what this angle is now? It's 30 degrees. Because, well, the number of ways to do that. If this angle is 60 degrees, then this angle is also going to be 60 degrees, and that should be 30. So 30 degrees. So the angle made by B with the vertical is 30 degrees. So all I need to do is now find the x and y components. So 105 is the absolute value of velocity. The x component is going to be in this direction, right? So it's going to be sine of negative sine 30i. Is that what you got?
Yeah.
Negative sine 30 degrees I. And the y component is going to be pointing upwards. So it's in the positive j direction. This is 30 degrees. So it's positive cosine 30 degrees j. So that's it. So VA with respect to B, when you do the math, comes out to be minus 37.5 I minus 90.93 J, and the units are feet per second. Okay, is that clear? Okay, so we are one step away from finishing this. We need to find acceleration of A with respect to B. Okay, and now for acceleration, there are multiple ways to do it. Well, what did we learn previously? We knew we're given the what we're given is the. So I did not write that down. So it's 90 feet per second for the velocity, and it is 15 feet per second square for the acceleration. And similarly for the other one, it's minus 25 feet per second squared because it's deceleration. So we're given the rate of change of velocity. Okay, so you can use we've learned acceleration in rectangular coordinates, polar coordinates, and then tangential or normal coordinates. Now the good thing about a circle is that the acceleration in the tangential normal coordinates is the same as the acceleration in the polar coordinates, because r and theta point in the direction of t and n. So we could use either of them. Let's just use the tangential normal coordinates. So AB is AA minus AB. Now this is given by ATUT plus ANUN. Okay, AT gives the tangential component of the acceleration for A. So let's look at A. The tangential component is basically 15 feet per second square, and it's pointing in a direction negative I. So that's minus 15I. So that's about it. That's the tangential component. The normal component always points towards the normal, towards the origin of the circle, right? And the magnitude is v squared divided by the radius. So it's going to be minus, because it points towards the origin. V square is 90 squared divided by the radius. In this case, the radius was 300 feet. So 300. Similarly, AB is going to be ATUT plus ANUN. That will also have radial and tangential component. So the tangential component is along the tangent along BB. We know that it is 15 feet per second, and the direction is going to be the same as the direction we had over here, right? So we know it's 30 degrees to the vertical. So it's minus 15 UT, and we know that this is 30 degrees to the vertical.
Doesn't I thought the acceleration was different for B, or it's decelerating
It's decelerating. Oh, it's 25.
at 25, yeah.
Okay, I just need to write this as 25. Good catch. Okay. So I wrote that as UT. I need to still find in terms of I and J, because everything here is in terms of I and J. And then the normal component is going to be V square. So the velocity is 105. So 105 square divided by 300. That's the radius, times UN. But UN is going to point in this direction, right? So it's going to be at 60 degrees to vertical. So what you can do is you can check, you can try, what we'll have to do is, yeah, question. Is it 300, right? Oh, I see it. Oh, my bad. It's 250, it's given to me. So it should be 250. So I'm going to just write this down and let you go. UT is minus sine, and you're going to check this later on, sine 30 degrees I plus cosine 30 degrees J, and UN is minus sine 60 degrees I minus cosine 60 degrees J. Once you put these values, you should get acceleration of A with respect to B is equal to 10.69 I plus 16.7 J